Today I'm going to tell you about another part of circles which are called chords. It's spelled the same way as like a musical chord. I don't know why it gets that name. I think I remember it. It actually does have a musical connotation, but I'd have to look that up. You can Google it. But anyway, chords, as you hopefully recall, are line segments that connect to 2 points on the circumference of the circle. And they have some special properties. First of all, I want to talk about congruent chords. So I don't think these are perfect. I tried to draw them. But let's pretend that those two chords are congruent and think about what that might mean here. With the center of the circle here, because all radii are congruent, think to yourself, what do you know about these two triangles that I just drew? If all radii are congruent, well, what does that mean? And it means that these two triangles are congruent by side-side-side congruency. And since the triangles are congruent, all their parts are congruent. So because we started with two congruent chords, that means that by CP/CTC, I can show that these two central angles are congruent. And because central angles match the arcs that they intercept, these two chords intercept this arc here. So this arc is also congruent to this arc. So congruent chords create congruent central angles and intercept congruent arcs. Okay, so if you see two congruent chords, you know that the arcs are congruent. The next thing is important, and we've actually encountered this a few times when we were doing constructions, and that has to do with the perpendicular bisectors of a chord. I drew two chords here, and in fact you could see that I could make a triangle out of it, but if I carefully draw the perpendicular bisector of those two chords to the best of my ability, so that it's both perpendicular and it's a bisector, like this, then guess what happens? The perpendicular bisector of a chord always goes through the center of the circle that the chords are formed on. And so the perpendicular bisectors of a chord always go through the circle's center. Really good. And then finally, see these parallel chords here? These are parallel lines, chords in a circle. Well, there's not a cool proof for this right off the bat, but what happens is you actually get congruent arcs. This arc and this arc are the same measurement, which means that this angle here and this angle here would also be the same measurement, these same central angles. But what's important to note is that the arcs are congruent. So parallel chords create congruent arcs between them. All right.